Hello, everyone. My name is Nicolas Vincentian, and alongside Christian Riveros and Domagoj Vroch, we submitted the paper Rematch, a novel regex engine for finding all matches to VLDB this year, and I'm here to present you that paper. So we start by introducing a problem that suppose that we have a regular expression and a document, and we want to find all matches of the regular expression in the document. So what do we mean by this? To give an example, take this regular expression here and that document there, and finding all matches in this example is equivalent to finding every substring of length 2 in the document. So the problem is that regular expression libraries do not capture every match in this sense. In the last example, a common regular expression library will only capture the first two A's and the third and the fourth in another match. This is the result of the semantics that regular expression libraries implement, these semantics being the lemma's longest result. So Rematch is an information extraction engine based on regular expressions that finds all matches, and it is implemented in C++ and can also be tested online in rematch.cl. So here's a screenshot of the web application that we have if you like to try it. So here's my outline, and we first in the paper introduce the RegQL, which is the regex query language for information extraction. This is the language that Rematch implements for its queries. Its syntax is very similar to standard regular expressions, with the main deviation being that we use this construct to denote the capturing of a submatch in a variable x. So here you can see we have the grammar, and it's very, very similar to what we have in standard regular expressions. Now, to understand the semantics, we will see some examples, and let's consider this document here that we have. The ant is an amazing architect. So suppose that we need to find every word that starts with an A. So we can have a RegQL query like this, where we first look for an space, then we capture a word starting with an A, and then we look for an space or a dot. And evaluating this on the document gives the words ant, an, amazing, and architect. Well, standard regular expressions use parentheses to capture submatches. Then an equivalent regular expression would be something like this, where we just replace our construct to capture with these parentheses. Now, suppose that we need to extract every two consecutive words, being a 2-gram, where each one starts with an A. In RegQL, we can use the last query and just duplicate it and concatenate both to give us this regular expression. And evaluating this, we get 2 grams for the words an amazing and the words amazing architect. Well, to obtain this result in regular expression, we must use look ahead operators. We don't have we don't have any other chance to do it without them. And finally, suppose that in the addition to the 2 grams, we want to extract the exact sentence where the match happens. So in RegQL, we have a possible query that does this. We have the last query from the last example, but now wrapped up in another query that finds a sentence. And evaluating this gets us the same result as the last example, and now capturing the whole sentence too. Well, what's interesting in this example is if one gives it some thought, is that regular expressions cannot get this kind of results. So continuing on the implementation, here we can see a little diagram of the rematch system with its models. We'll start off by reviewing a bit the rewriting model. So for that, we must introduce what a logical variable set automaton is, and what is it? What it is a finite state automaton whose transitions are labeled with letters and variable markers. These are for opening and closing a variable. So, for example, if we have this query here, then a logical VA for it would be something like this. And notice this transition. This is for opening a variable, and this is for closing a variable. So the rewriting model's purpose is to parse the input query and build a logical VA for it. Next up, we have the filtering model. And here we'll explain by example the main idea behind it. Consider the query from the last example, and the query and the document. And we will say that a segmentation of the document is a set of segments that split the document in some way. In this example here, we see a possible segmentation of the document marked in green. So why do we define this? Because we are interested in what we'll call a valid segmentation for the query over the document D. By the example, we can intuitively guess that a valid segmentation happens when every output is contained in the segmentation. So the filtering's model purpose is to quickly find a good segmentation that is valid for the query over the document, and this in order to later reduce the load on the main algorithm. Next up, we have the output model. And well, in Rematch, we will represent mappings in terms of output sequence. So here we have we have a list of mappings, and we can see the mappings mapping the variable to some spans with positions in the document, and we can represent them in terms of output sequences like this, like in pairs of variable markers and document positions. So in Rematch, what we have is that we have a data structure to store these output sequences and then later enumerate them, that we call the enumerate compact set. And that is what it is a DAG, directed acyclic graph, that we can see here, that will store the output sequences. So this is an ECS that actually stores these output sequences, and it stores them by using the paths, the possible paths in the graph here. So ECS is important because it allows us to understand, to enumerate the output sequences with output linear delay. Next up, we have the determinization model and evaluation models. For that, we here have the main algorithm, the main evaluation algorithm. So the evaluation algorithm builds the ECS while reading the document and then enumerates the output sequences with output linear delay. And it accomplishes this by simulating the runs of the determinized logical VA, which is computed on the fly. So now we have some benchmarks here, some results for the implementation of Rematch. First off, we see that we did some experiments with different with different data sets here. And we have different data sets, and well, the main purpose of or the main approach that the paper has is actually to build up on the different optimizations that Rematch has. So here we see a list of optimizations that we didn't mention in the presentation, but what is important here is that we first have a naive version of Rematch, that this being a version of Rematch that does not implement any optimization. Then we see a list of versions that only implement one optimization. And finally, here we see a version of Rematch that has all optimization, being the official version of Rematch. And the key takeaway here is that different optimizations do better in different scenarios and in these data sets. But overall, each one of them contributes to the performance, the runtime performance of the final version of Rematch. In the other set of benchmarks that we did, we compared Rematch against several popular regular expression engines. The main takeaway here is that given the fact that Rematch being a simple implementation that we developed and being also more powerful than the other engines in the sense that it can find all matches, it still performs quite competitively compared to the other engines in our data sets. So to end up and share our conclusions, well, the first conclusion would be that standard regular expression semantics do not output all possible matches of our regular expressions. With Rematch, we show that it is possible to build a regular expression engine that captures all matches efficiently with output linear delay. And we also showed that Rematch, the implementation of Rematch, is competitive with other regex libraries, and that it is the only one that captures all matches. Thank you so much for your time, and that's it.